Hello, and welcome to AISC's Night School Fundamentals of Stability for Steel Design. This is presented by members of the Structural Stability Research Council, and today is Session 3, Behavior of Flexural Members. My name is Patrick Newman, and I am with the AISC Continuing Education Group, and I'll be moderating today's presentation. I would like to introduce today's speaker. Ron Zimian is a professor of civil and environmental engineering at Bucknell University. In addition to authoring papers on the design and analysis of steel and aluminum structures, Ron is co-author of the textbook Matrix Structural Analysis and the editor for the 6th edition of the Guide to Stability Design Criteria for Metal Structures. He is currently chair of the Structural Stability Research Council and AISC's Task Committee 10 on Frame Stability. And he recently completed his term as chair of AISC's Task Group on Inelastic Analysis and Design. He serves on the AISC as well as the Aluminum Association Specification Committees and is active with the Steel Joist Institute. In 1994, Ron was awarded the ASCE Norman Medal, and in 2006, he received AISC's Special Achievement Award. Last month, Ron received ASCE's Shortridge Hardesty Award for his substantial accomplishments in research and service and teaching, as well as advancing practice in the field of structural stability. And with that, I would like to turn it over to you, Ron.
Well, thanks, Patrick, and good evening, ladies and gentlemen. I'd like to begin by again mentioning that the Structural Stability Research Council is very pleased to be joining AISC and delivering one of their night school courses. As the title of the course indicates, we are focusing on the fundamentals, so just the basics. Tonight, we transition from studying compression members to having a look at flexural members. I will give an overview on the fundamental behavioral aspects, and next week, Todd Helwig will provide the related design lecture. So let's get started with the strength limits of flexural members. So here on this slide, I've kind of listed them for you. It should feel a little bit like deja vu all over again when you take a look at this in the compression members. And that's sort of a hidden point tonight, is it'd be really nice if you could draw an analogy between the two. So certainly limit states of flexural members, we could have full yielding of the cross-section, and we'll take a look at that. And then, of course, we move down to instability. And here we're talking primarily one of two possibilities, one along the member length, and we're going to have a look at that tonight. And that would, of course, include lateral torsional buckling, which could either be all elastic or with some yielding or inelastic lateral torsional buckling. The other instability, which we won't have a look at tonight, is at the cross-section. So we could have some form of local web or flange buckling, and that could certainly reduce the strength of our flexural member. But usually we're working with compact sections, and although we do have to check and confirm this compactness, we usually stay out of jail pretty easily for the fundamental designs. So let's have a look at full yielding. To begin with, I showed this slide in session 1. All the way back to basics, we do a tension test, and we plot stress versus strain. And sort of showing two curves here. The blue curve is the more realistic curve in which we would come up. Well, everything would be nice and linear at first. We would eventually yield the material. We'd have some form of a yield plateau. And then we get some strain hardening, and the strain hardening would eventually reach an ultimate strength, and eventually the tensile coupon would rupture. Now, one thing I want to just mention is that this slide is in no way to scale. If this was 1 unit here, this would be approximately 10 units, and this would be approximately out here 100 units. So you've got quite a bit of ductility in steel, and so we try to take advantage of that in the design of steel structures such as flexural members. So now one of the important things to note is that that was done for a tension test. There have certainly been compression tests done, and the behavior is similar enough, although you don't get rupture, of course, but sort of this elastic plastic. So we tend to assume that the yield strength in compression is the same as the yield strength in tension. And so the other thing that's going on is we also, in steel design, neglect this strain hardening effect. So we come up, we let the thing be elastic, and then once it's yield, we assume there is no stiffness in the material, and it's just perfectly plastic. So if we apply this now to looking at the bending of a beam, in the lower right here I have a small schematic. What I'm going to do here is take a member that's very short, so there's no possibility of any form of buckling. And let's say it's also compact, so there's no possibility of any local buckling of the flanges of the web. And I'm going to subject it to a moment, and I'm going to measure the rotation. So I'm plotting then on these axes the rotation according to the amount of moment that I've applied to this short member. Well, at first, as you can imagine, everything is nice and elastic, and the stiffness is basically EI for the entire section. So if you look over here to the right, our stress profile, the normal stresses are distributed for your MC over I. But eventually, as we apply enough moment, the section will begin to yield. So in this case, for major axis bending, the yielding would start at the top and at the bottom of the beam. And that yield moment would occur at the product of the elastic section modulus S and the yield strength sigma Y. Once that yielding occurs, it sort of starts moving through the depth of the member, both coming down from the top and up from the bottom. And like I said in the previous slide, the section that has yielded, we're going to assume has no stiffness. So the E value up in the top and bottom would be 0. But the remaining of this portion of the member still has plenty of stiffness and can certainly resist additional moment. But you can see the reduction in stiffness is shown here as a response that the slope of this M theta diagram has been reduced. Well, even though we've got what we call some partial yielding, the section is yielding a bit, we can still resist additional moment, so we keep applying moment. And eventually what's going to happen is we're going to move through a point in which we've fully yielded the top and bottom flange, and the only thing there now resisting moment, but it still is doing it, but resisting the moment is the web. Eventually, once we lose those flanges, it's quite a hit, so we've lost quite a bit of stiffness now, but eventually we'll completely squeeze out all the elastic strength of the member, and we'll get full yielding. And at that point, according to our assumptions that we're not going to include any strain hardening, we've basically have no stiffness left. And with no stiffness, we're going to get an unbounded amount of rotation. Now, one of the things that I'd like to point out is that when this full plastic hinge or the full plastic moment capacity is reached, it's nowhere near as dramatic as one might think. Nothing exciting really happens. And in fact, I tried to show you a picture here that I grabbed out of Bill McGuire's Steel Structures textbook that shows a plastic hinge. So what's happened here is who's ever running the experiment has whitewashed the steel member, and where the strains are large, top and the bottom, the whitewash is flaked off, and you can see that this is pretty much what a plastic hinge looks like. So it's not very exciting, or certainly very dramatic. The other thing I'd like to say is that my diagram is a tad out of scale. If you take the plastic section modulus, the ratio of the plastic section modulus to the elastic section modulus, some folks tend to call this the shape factor, it's really only about 1.15, at best maybe 1.2 for the type of wide flange shapes that we might use in design. So that means that this point is really about 5/6 of the way along to this moment here. But just so you folks could see it, I sort of separated a bit. Now the picture is different in minor axis bending, but we're not going to be going there tonight. So it appears then that we're all set to take our first crack at defining a beam curve. And basically what a beam curve would be is if we were to plot the strength. So here over on the right I have a moment being applied to a beam. And I've got those moments, one at each end, they're equal and opposite, being applied to a beam of some unbraced length L sub b. If that's all we're going to work off, we're going to say, all right, every beam out there, no matter how long its unbraced length, it can reach the full plastic moment capacity. Life would be great, and this is what we'd be looking at for a beam curve. Now, interesting enough, if we were to turn that beam sideways and there was no possibility of any type of member instability, then that's exactly what the minor axis beam curve would look like. But in the major axis world, I think we'd probably realize that it's not acceptable. If the unbraced length is of any significance, there exists the possibility that the member itself may simply buckle. And that buckling could occur, like I said, either along its length, or there still exists the possibility of a local buckling, but we're not going to go there tonight. So we are going to focus now then on this sort of member instability. So a little bit about what's going on there. So I've sort of made the cartoon a little bit larger so you can see what's going on. What I'd like you to do is focus on this simply supported beam. Like I said, it has equal and opposite end moments. And so if you were to actually plot the moment diagram for this, it wouldn't be very exciting. It would just be a constant value all the way across. Now the top of the member, the top flange is all in compression, always, and the bottom flange is always in tension. Now another important thing in my diagram, and this is sort of essential here, is that the ends are braced. If they weren't braced and we put any type of load on here, there's a good possibility the beam might just tip over, fall over in the minor axis direction. But we do have these sort of rods here that symbolically are representing the fact that the ends of the member are prevented from twist. It's simply supported. So as we apply this moment at each end, initially that beam is going to bend downward, and what would happen is we'd get some vertical deflection. All right, so in the diagram I'm showing here, here is sort of a cross section, and with no moment on there, the beam would be up here, and we put some major axis bending moment on it, and the beam in the center would come down. All right, so that wouldn't be too bad. But things get a little bit more interesting as we keep increasing those moments. And like I said, that top flange everywhere, all the way across, is all in compression, and as we know from lecture 1 and 2, that when something's in compression, it wants to buckle. All right? And in this case, it has one of two possibilities. It could either buckle up and down, which would require us to, when it buckles, bend the section about its major axis, or it could buckle about its minor axis, and that's certainly the smaller path. So down on the right here, I show this cross-section now, and it's a bit in turmoil. The top of the beam, which is in compression, wants to buckle laterally. It wants to move over out of plane, if you will, out of the plane of the beam. But the bottom flange, which is all happy and in tension, just wants to stay right where it is and remain straight. So they go at it. So who will win? Well, like any good relationship, it ends in a compromise, but somebody gets the better end of the deal, causes more trouble, and in this case, that's the compression flange. So after we've put enough moment on here, what will happen is that compression flange will buckle outward. It will take the tension flange or the bottom flange with it, but the bottom flange does get some say in the matter and does pull back a bit. So when that compression flange buckles, it moves the entire section over. But like I said, that bottom flange says, well, I don't want to go over there, so it pulls back, and you also get some twisting. So we've got lateral movement, and we've got twisting or torsion, and this is your fundamental lateral torsional buckling. And I've got a couple of slides here just to show you some photographs. Now, I'm sworn to secrecy on providing any details about where these photographs are taken, but I do think that they do demonstrate some nice behavior here. First, up in the upper right, showing all these different cross sections. So all these sections, when you subject them to some type of major axis bending, are all susceptible to lateral torsional buckling. Now looking down, let's take the slide on the lower right. The system was designed for an upward force. So if we put an upward force on this beam, the bottom flange would be in compression. And it was quite happy and well braced, and it wasn't going anywhere. Unfortunately, at some point or another, things went wrong, and the system was run incorrectly. And at that point, instead of there being an upward pressure, there was a downward pressure. And when this downward pressure occurred, just the opposite happened. Now the bottom flange was in tension and the top flange was in compression. And as a result, the top flange is all in compression. There's nothing bracing it. And we got this mode like I was showing you in a cartoon in the previous slide, but this is an actual real beam now in a mode of lateral torsional buckling. Now, lateral torsional buckling doesn't just need to occur in wide flange shapes. I found this picture on the web, and here's one of those temporary bridges that every once in a while we have to drive over, and it appears that it wasn't a good day for this one. And you can see that the bridge is basically set up so that the two sides here are the beams, and the top accord of this beam on the left side, say, is all, of course, in compression, and we've got some lateral torsional buckling in this extended long beam. So lateral torsional buckling doesn't just occur in wide flange shapes or channels or something. It can occur anywhere from steel wide flange shapes right up through steel joist, right up through entire temporary bridges like this one here. But nevertheless, this whole concept of lateral torsional buckling certainly deserves your attention. So what I'm going to do is we're going to spend a few minutes on computing the theoretical bifurcation load, and we're going to go and have a look at the assumptions that we made as well. Now this is something we did actually in lecture 1, and I did this for the Euler column. So if you can almost see the direct analogy here, we're going to do it now for a beam. But then what I'd like to do is undo the assumptions that are really pertinent to tonight and try to approach the reality of the situation. And so that might include not just assuming the material is elastic, but allowing for some partial yielding, and looking at other loading conditions besides that that uniform moment that we're applying, and even other support conditions. What happens if we provide a brace somewhere along the span? My lecture tonight is then going to wrap up with looking at the AISC beam curves, and we'll have a look at some of the others throughout the world as well, and some comments on what we're saying. So that's where we're at.
Ron, before we move on, we did get one question that's kind of a good basic question for us, and that is, when we're talking about restraining for rotation, are both the flange and the web restrained for rotation? Okay.
I'm actually going to get in that later in my lecture, but I tend to think that the way you can think about these braces is twofold. One, bracing for twist, and bracing for lateral movement. All right. The bracing for twist is the most important one. What you're trying to do is prevent that relative movement from occurring. Now that's not to say that if you could somehow hold on to one member and prevent some lateral movement to one portion of the member, maybe the compression flange, that because the tension portion is also acting against you, that you couldn't improve situations. But the real crux of the matter is to provide a good solid brace, you really need to resist twist. Now this is going to be followed up in great detail in our lectures 7 and 8. So whoever asked that question, you're going to get some real good information on how to design those braces and what that behavior really is in a couple of lectures from now.
Okay, thank you.
All right, so let's have a look then at computing the bifurcation solution to lateral torsional buckling. Now that's not fair. We can't see you, so if you just ran out of the room, get back. That's I think it's really important that you see this once all the way through. I think what I really would like to achieve here is to show you that the mathematics is not a complete nightmare. It is actually pretty straightforward. You don't need to derive it yourself, but at least to have these lecture notes on hand somewhere and be able to look back at them and say, oh, okay, yeah, I could have done that. I hope you would find rewarding. And it also is going to sort of point out some of the important assumptions that we undo as we try to provide you design provisions in the AISC specification. So with that big pitch, let's go and see if we can develop the bifurcation solution. Now, in Lecture 1, I mentioned this word bifurcation. It's important to note that basically what we're talking about here is a form of instability, and now you might even call it theoretical, in which when the moment is at a small value, say less than our elastic buckling moment, the beam is quite happy and just flexing a little bit downward. But then suddenly there is this trigger point, this instantaneous change in which we go from this shape to the shape down at the bottom in which we are in the buckled shape. So that by definition is what bifurcation is. And again, I'm trying to show you that lateral torsional buckling mode. So we're going to develop that theoretical what is M sub E in which we finally move from no lateral torsional buckling to a beam that is laterally torsionally buckling. Now to do that, we need to make some assumptions. The first one I think we could probably live with, and that is that we'll be looking at prismatic members. We can certainly come back to this later once we've mastered it and make the moment of inertia a function of the length and have a go at those differential equations. But for now, let's just assume that it's a prismatic member. The member size is not changing. The other thing, and this is important, is that we're only thinking about major axis bending here. So there is no out-of-plane behavior at all before the buckling, and once the buckling occurs, of course, it is out of plane. But up to the point of buckling, it's all just major axis bending. We're going to assume linear elastic behavior. This means that the modulus elasticity E is a constant, and we'll take a look at modifying that. Uniform moment distribution. Again, I indicated this earlier. The moment diagram, if you were to draw the moment diagram for this applied moments equal and opposite at each end, you would get, like I said, just a straight line. There is no slope. So that would be uniform moment case. At this point, we are braced at the ends and frictionless, so we just have these two braces, one set on the left end of the beam and one set on the right end of the beam. Like I said, later in this lecture we'll go and start undoing these assumptions, but for now, let's hold on to those and see if we can get ourselves a bifurcation solution. Now before doing that, I think it's always good to just do a little bit of what I might call a parametric analysis, and that's to just sort of guess what terms are going to be involved with this and whether they should be sort of in the help us, that would be the numerator side of the equation, the upper portion of a fraction, or hurting us, and if they are, then they would probably be in the denominator or the lower portion of any fractions that we have. So what might we expect? Well, if we take a look at that buckling mode on the right, we're probably, in fact, we are getting sort of a combination of minor axis buckling, and as we saw in lectures 1 and 2, minor axis buckling would be a function of the E, the moment of inertia, about the minor axis, and the unbraced length. Okay. And again, that unbraced length is going from this braced point over to this braced point. So we'd certainly expect those in our equation. Now torsion, we're seeing that twist, so we need to think a little bit about torsion. And a lot of folks haven't had a good experience with torsion, so I'm going to slow down and talk a little bit tonight about torsion. But for those of you that are whizzes at torsion, we've got basically two types, the Saint-Venant torsion, and as you may recall, it's a product of the shear modulus and the Saint-Venant constant, or torsion constant J, and again the unbraced length. Now there's another aspect to torsion called warping, and we'll have a look at that in a bit, but if you're a whiz at warping torsion, then you would know that the critical components are a material, the E value similar to G, and a geometric constant, the warping coefficient C sub W, and of course it's also a function of the unbraced length. Are there any other terms that we'd expect in the solution? Well, anytime we're solving differential equations, we're always ending up with sines and cosine solutions, so of course pi is going to end up there as well, and so that person's always showing up to the party. Anyway, so what's their impact? Well, with respect to the material, I think it could be relatively easy to digest that if we increase either the modulus elasticity or the shear modulus, which is often directly computed from the elastic modulus, that we should be increasing the capacity, the elastic LTB capacity. Likewise with the section properties. What did we have from looking above? We had the moment of inertia about the minor axis, the St. Venant torsion constant, and the warping torsion constant. And these are all geometric parameters, and if we increase them, then, well, we would expect the elastic buckling moment to also increase. The only term left then is the unbraced length, and just like a column, the longer or the larger the unbraced length, then probably the easier it is to buckle. And so that's where we would expect. So when we go back later and after we have our solution, we'll sort of say, hey, how did it go? Did our material and section properties end up in the numerator, and our unbraced length always end up in the denominator? So we'll have a look at that in a bit. So with respect to minor axis buckling, we certainly saw this in sessions 1 and 2. You're well aware of Euler's buckling equation, pi squared EI over L squared. So you're probably up to speed on that, and that doesn't frighten you too much. But like I said, to study lateral torsional buckling, we've got the lateral part down, but the torsional part, we need to know a little bit about torsion. And St. Venant, well, you've probably heard about St. Venant torsion and used that before, so that would just get one question mark, sort of a, yeah, I think I remember that. But for many of you, the warping torsion, what is that? And so I'm going to spend a few minutes on that as well. So let's start with the St. Venant torsion. This is the one that you pretty much learned in your solid mechanics course. What I've done here is taking a section, a length of a wide flange section. The length of the section is dx, if you will, and I'm subjecting it to a torque. The far end is fixed at where it is, and the end closest to us twists. And so what I'm measuring it is the amount of twist that I get d theta dx. So for each little length d theta x per unit length dx, the amount of twist that we would get is T over Gj. So this is the St. Venant torsion, Gj over L that you're so familiar with, and I've just sort of rewritten it here. So that's certainly an important part of our torsion. Now, unfortunately, life for open shapes is not as wonderful as it is for life in closed shapes when it comes to St. Venant torsion. So what I wanted to do is just show you a little bit of math here comparing the two. On the right, I have an open shape, wide flange shape, and when this thing is subject to a torque, the shear, the shear stresses develop to resist that torque, and those shear stresses I'm trying to show here as little blue arrows, and they march around and cause a resisting torque, sort of as I'm showing here. All right. Now, if you were to calculate the torsion constant for this section, it's basically the equation you've always used, and that is the sum of bt cubed over 3. So B would be, for example, the flange width, and T the thickness. B would be the depth of the member. T would be the thickness of the web, and then we'd have also a bt cubed for the bottom. We'd add them up, and that would give us our J value. Now things are a little bit more wonderful for a closed shape. What happens here is the shear stresses are allowed to align all the way around the section. So by being a nice continuous cross-section like this hollow circular shape I have here, you get a lot more bang for your dollar. The shear stresses do not need to go opposite of each other throughout the thickness. They can stay in the same direction to resist the applied torque. Now a little bit more mathematics, and what you would find is a kind of a nice approximation for the torsion constant here is 4 times the area enclosed by the median. So if we were to put a line right down the center of our cross section, the area enclosed, sort of the pi r squared of that area is what A hat is. So we have 4 times that area enclosed times the thickness, the wall thickness, divided by the circumference at that median spot. And so if you're having a look at that, you're thinking, whoa, so the enclosed area is getting squared. So you're getting a lot of J. Compared to, there's really, the only thing that's getting cubed or anything amplified here is the thickness, and that number is usually pretty small. So you're taking a small number and cubing it, it's getting even smaller. All right. So anyway, I start with what I thought you might like to see is the difference between the torsion constants. So I'm going to take here a W8 by 13. All right. Its flange thickness is 0.23 inches. Its web thickness is 0.26. I calculate the cross-sectional area, or just look it up in the manual. It's 3.84. And if I use my BT cubed over 3, the summation of the BT cubed over 3 for each one of the 3 plates, top flange, web, and bottom flange, I get a J value of 0.0871. So what I decided to do then is I'm going to take and use a thickness of about the same, 0.23, 0.26. So I'll go with a thickness of about 1/4 of an inch. And I'm going to use the identical area. So as far as material being used between the hollow shape and the wide flange shape, they have the exact same area. And so if I have the thickness in the area, what I can then do is back calculate the diameter. Once I've got the diameter, then I can go in and I can actually calculate using this equation up here, 4 times the area enclosed. Now again, this isn't the cross-sectional area of the tube, but the area enclosed within a line that runs down the middle of the tube all the way around. And so 4 times that pi, 4.9 squared over 4, so that's the area enclosed, squared, multiplied by the thickness, which was 1/4 inch, divided by the circumference, which is again the length all the way around, which is pi d, or 2 pi r. Throw that math together and I get a J factor of 22.95. So here are 2 sections, one open, one closed, the same area, same material used, but the J here is 0.0871, but over on the left here the J value is 22.95. So that's a factor of 264, and that is very significant. So the bottom line here is closed sections rule in torsion. So anytime you have a torsion problem, think closed section, because you're going to get a lot of bang for your buck by enclosing area. The other thing to note is our lecture is going to tonight focus on wide flange shapes, but I've often been asked, why doesn't anyone ever make a big deal about lateral torsional buckling of closed shapes, HSS shapes? Well, by and large, the J value is so large that it's nearly impossible to get those sections to twist and buckle. They pretty much just form a plastic hinge. Anyway, so that's the story on St. Bernard torsion, open shapes versus closed shapes. And you might be sitting here thinking, oh my gosh, life is terrible. We use wide flange shapes all the time, but what are we going to do? Well, as it turns out, there's somebody else involved, and that's this warping torsion. So I wanted to just give you a quick overview. A lot of you may have tried in grad school to understand warping torsion. It's a delight to try to do that. Vlasov theory and all that comes to mind. But I'm going to try to give it to you in a very watered-down version, and especially just for a wide flange shape. So warping torsion, this is what I hope, if you're not aware of this, this is your new best friend when it comes to torsion of wide flange shapes. The thing here is that we take this shape, and I'm looking at it in 2 possibilities. One, I'm looking at the wide flange shape from the top, and in this view here, I'm looking from the end view. So either from the top view or the end view, I apply some type of a torque. And because, let's say, that the right end of this wide flange shape is fixed, what happens now is that the top flange actually bends downward just like a cantilever beam would, and the bottom flange bends upward. So that cross-flange bending does a world of good when it comes to resisting torques. And so this warping torsion is actually, like I said, your new best friend in wide flange shapes. So let's have a slightly closer look at how that cross-flange bending, is related to the applied torque. So things get a little bit mathematical here. So warping torsion and its relationship. So over on the right, what I've done here is I've taken that same shape that we were looking at for St. Bernard torsion. It's dx long, and we're going to get a rotation d theta x along its length axis. And I've applied a torque, and let's go to work. So we apply that torque, and that torque can actually be decomposed into a couple of shear forces that are acting in the top and bottom flanges. So remember, we said we had cross flange bending. If we have cross flange bending, we have shear force. And so here I'm showing the shear force directed this way, being applied by that torque of Vf, the shear force in the flange, and I have a shear force in the bottom flange. The distance between these two forces, so these two forces are in opposite direction, and they produce a force couple, and the distance between them is h. So no matter how you look at it, that torque then is resolved into the shear force in the flange times the distance between the flanges, or Vfh. Now we know that the shear force is the first derivative of moment. Okay, so the slope of the moment diagram is the shear. So Vf is the derivative of moment. So what I'm going to do here is I'm going to, looks like I have one other term in this as well. I also know that the bending moment in the flange, this is from our moment curvature relationship, is equal to EI of the flange times the second derivative of the sort of deflection in this out of plane direction. I can define dW, so I'm just setting up a couple of values here, and I'm going to substitute them all into the top here in a moment. Now if we go over to the diagram in the right, if we take h over 2 and we multiply it by the angle sweep d theta dx, d theta x, we would get dW. So that's that term. So plug and chug, I start inserting all of these values into this equation up here, and what I end up with then is kind of an ugly looking differential equation down here, that the torque being resisted by warping torsion is equal to EIF h over 2 times the third derivative of the theta x to the length times h. All right. So we've got that equation. Ugly, I agree, but it's really just coming from some basic mechanics in flange bending. So we went from here to here. At this point, we can introduce what's called our warping coefficient. So if we multiply IF times h over 2 times h, we can define what is C sub W. Another simplification is, if you think about we're bending that flange about its sort of strong axis of the flange, which is really the minor axis of the section. And the minor axis of the section is basically made of the moment of inertia for the minor axis of the section is basically being produced primarily by the flanges. About half of that minor axis bending moment of the section represents that flange IF. So with a few substitutions here, we can see that in this equation is provided, I think, in a user note in the specification, that the warping constant is actually IY h squared over 4. So we've now got this geometric parameter at least approximated for a wide flange shape for you. And we've also got the torque being resisted by warping. So a quick summary, where are we at? We have two torques participating. The St. Venant torque, which we know for the wide flange section is probably pretty small, but it is playing a game. And we have the warping, which is significant, and we just derived that equation there. And again, it's directly related to the warping coefficient CW and the modulus elasticity of the material. So the total resisting torque then has got to be the sum of these two. So that's who's helping out when it comes to torsion. The St. Venant is contributing and warping is contributing. And like I said, for a wide flange shape, the warping is a lot more significant than the St. Venant. So I've got these two expressions, and I substitute in, and I've got now a total for the resisting torque. So that's my brief 20-cent lecture on torsion. It's probably been a while since you looked at torsion, so go back and look at these slides, but I don't think there's anything here that's too alarming. And again, for most of us, we haven't really thought about warping torsion lately, and I hope I've watered it down to as basic as you can. But please do go back to the slides and have another look if need be.
Ron, we did have a question on torsion.
Okay.
And that was, for a circular shape, does the polar moment of inertia equal the torsional constant J?
For a circular shape, it does. For any non-circular shape, it does not. The polar moment of inertia, by definition, is the Ix plus the Iy, and you should find for a circular shape that that sum is the same. But for all other shapes, you'll find that the product of those two, the sum of Ix and Iy does not equal J, the torsion constant for the other ones, the other
Okay,
shape.
thank you. Thank you.
Oh, sorry, got ahead of myself here. So we've had a brief course on torsion and on lateral buckling. So now it's time to pony up, and let's see if we can actually solve for this elastic critical buckling moment that is producing lateral torsional buckling. Like any good mathematic derivation, we're going to need a coordinate system. So I'm going to define x as along the length of the member, y is vertical, and z as out of plane. And the out of plane z direction accompanying it is a deflection function, which we'll call w of x. So I've got these moments, and the first thing I'm actually going to do is resolve them. So a little bit of math here. So here I am. I'm going to make a cross-section cut somewhere along the length. And we know the moment at that point, the resisting moment about the major axis has to be ME. But the section has twisted. And it's twisted by some amount theta x. All right, so let's some amount theta x. So if we have along the span, we've got ME being applied. So here I've changed conventions a little bit just so it's a little bit easier to see, is I've gone from showing moment as being sort of this circular force to a double arrow, but it's the same thing. So this double arrow means moment about this z-axis. And that moment about the z-axis we're going to resolve into two components, just like we'd resolve a force into two components. One component perpendicular to the member, all right, that would be mz prime, and that would be me times the cosine of theta. And the other component, which is the vertical component, my prime, and that would, of course, be me times the sine of theta. Now, keep in mind that we're talking at bifurcation, that it's just buckled and the deflections are very small. So this theta is very small, and so the cosine of theta, or the cosine of a very small number, is 1, or very close to 1. So we'll approximate it as 1, and that's mz prime is just me. But it's really this second term that we're after, and that is the approximation for the sine of theta. So if you have your calculator and you pipe in the sine of a very small number in radians, you're basically going to get back that number in radians. And so that is the moment, is that when theta is small, the minor axis bending moment. And keep in mind, that's what's related to our lateral torsional buckling. The minor axis bending moment is the elastic moment that we're searching for times the rotation wherever we're at. Now another shot here, and this so we need, so lateral torsional buckling, it includes two components, right? Lateral movement means lateral bending and torsion. So let's have a look at what's going on with respect to torsion. Now to do that, I'm going to go from our previous picture, which was a nice 3D model, to looking from at a top view. So just to get yourself oriented, here we are running along the length of the beam in the x direction. This was the out of plane z direction. Here's the moment being applied down at one end, and here's the moment being applied at the other end. And what I'm going to do here then is make a cut, and just like we did in the Euler column, I'm going to create and look at this free body diagram. So at the bottom I've got the applied moment, which is the buckling moment. And now what I can do is somewhere out along the length of the member, I do know the angle, and that's just the dw dx. Remember that w was the deflection in the z direction. So the slope of the member is the angle that we've got. And if we've got that angle, then we can resolve this resisting moment into its two components, the major axis bending moment mz prime and the torsion. Okay, so again, we're after this torsion piece. So the major axis bending moment would be me times the cosine of theta. So it's this piece of it. Alpha, and alpha is very small. Again, when this thing buckles, we've got just a little bit of movement out of plane. So the cosine of a small angle is 1. So mz prime is just the elastic. But it's really the torsion that we're after. And the torsion is the applied moment me times the sine term. Okay. And the sine alpha term then, alpha is small, and so the sine of a small number is a small number, is that number. And so we can approximate then the torsion as the elastic moment times alpha. And again, from the top of the slide, we said that alpha up here is really the slope of our member, the lateral slope, which was dw dx. So that gives us the torsion. So we've got we've got two things going on. In the previous slide, we took the elastic moment, and we've got now the minor axis bending component. And then in this slide here, we took the elastic moment, and we have it now in terms of the torsion. So those are the two things, minor axis bending moment and the torque. Okay, so first let's have a look at that torque. As I said, the applied torque, if you will, the elastic moment buckling the member from the previous slide was me times dw dx. And then based on our short course on torsion, we have two resisting torques, one produced by the St. Venant and the other by the warping. So I've just made a substitution there. So if you will, at this point, we've got what's starting to look like a pretty scary differential equation. And strangely enough, what we're actually going to do is we are going to take a derivative of that. And you might say, well, what the heck? That sounds pretty bad. But there's actually a good reason for doing that, because dw, the second derivative of this thing, is actually related to our moment curvature principle. So getting that second derivative is our friend here, even though it makes for a slightly uglier differential equation. So here we are now. We're at this point. All right, and I know you think, oh God, is this thing ever going to end? And it does. We're pretty close. So let's move to the next slide. So this is where we were from the previous slide. Now, 2 or 3 slides ago, we had an expression for the minor axis bending as a function of that applied moment me. And that slide showed us that me theta about the x-axis is what my prime is. But this my prime is also equal to, based on our moment curvature relationship, eiy times the second derivative of the deflected shape in the z direction. So from that moment curvature relationship and the sort of resolution of moments that we did, we can actually solve for this second derivative, and it's equal to, the second derivative is equal to me over ei times theta x. And we can now make a substitution for this term right here and for this term here, and we end up with this. Now, why is this great? Well, finally we've got ourselves a differential equation that is all in terms of theta x. So we got theta x, we got the second derivative of theta x, and the fourth derivative of theta x. Where before, when we were at this differential equation where we thought we were at the end, two of the differentials was in terms of theta x, and the other one was w. So this last little dance provided us with a nice, happy differential equation. So I showed in the first lecture that you could go now to some type of program. Again, our students today don't, break out, roll up the sleeves and actually solve the differential equations by hand. They use some type of a symbolic processor. I think I showed you the Wolfram solver last week. You could fire it up again and use this one. And if you would actually solve this differential equations and then apply some boundary conditions, you'll actually get a solution for the elastic buckling moment. Now, the boundary conditions I just want to point out to you are sort of twofold. One is that the rotation about the x-axis, so again, the rotation about the x-axis, which is the twist, is 0 at x equals 0, and 0 at x equals out at the other end. The second derivative of the displacement, of the rotation rather, which is again directly proportional to the second derivative of the minor axis bending moment, is also 0 at the two ends. So we know that we've got sort of a pin here in the minor axis at each end. That was the second derivative of w with respect to x, and we show that it was directly proportional to this theta of x. So we've got our boundary conditions at each end. Substitute those into the solution of our differential equation, and this is what pops out. So now, are you expected to derive this all on your own? No. But I think if you just follow the math, there's really nothing too alarming here that you should be saying to yourself, there's no way I could ever believe this. It's pretty straightforward, and I've tried to water it down the best I could. Now, I think it's kind of fun if you actually take a look at our solution. I'm showing the square, the elastic moment squared, because by doing that, you can see two parts. The first is the pi squared EIY over LB squared. My gosh, that was exactly what the minor axis buckling force was from our previous lecture. So you can almost think of that. There's the top flange buckling. The second term that comes out is representative of that tension flange causing kind of a resisting torque. And who's in the equation? But of course, who we would expect, the St. Venant torsion and the warping torsion. So it seems sort of, yep, everyone is there. Now, if I get a little bit more mathematical and just take a square root of both sides, I can solve for them the elastic buckling moment, and we get an equation that looks like what's being shown on the right here. Pi over LB times the square root of the quantity EIYGJ plus pi EI over LB squared times IYCW. So we've got kind of two pieces here. We've got the St. Venant piece and the warping piece, and appearing in both of them is our minor axis bending terms. And the thing to note is, we did that parametric study earlier on, and we can see that the E and the G is always in the numerator, and the IY and the J and the C sub W is always in the numerator. So we were spot on there, and the elastic critical buckling moment is inversely proportional, not directly inversely proportional, but inversely proportional to the unbraced length. So the longer the unbraced length, the greater the smaller the elastic buckling load. So hurrah, we've got ourselves to a great milestone here. We now have an equation for the elastic lateral torsional buckling. So just like with that column curve in Lecture 1, we've now got a second chance at creating a beam curve. Depending on the unbraced length, if the unbraced length was fairly short, we could fully yield it before elastic lateral torsional buckling would occur. If the unbraced length was fairly long, before we could fully yield it, we would get some form of elastic lateral torsional buckling to occur. But the big question is, all right, time to undo those assumptions, because we've got several assumptions especially related to this M sub E. Okay, so let's go into the lateral torsional buckling and start undoing those assumptions. All right, so let's have a look at them. So this is the slide that I showed earlier. We're going to let the member stay prismatic. Let's not get too crazy tonight. But the one that I wanted to have a look at is similar to what we did with the column a couple weeks ago. And that is this assumption that only major axis bending occurs before bifurcation. Now that is a fact for bifurcation, but in reality, there's probably some type of an initial imperfection in that member, and as a result of that initial imperfection, we'll probably get some bending. So that's more or less what I'm saying in this slide here, is that even right from the beginning, there's either an initial imperfection there, or that there's some form of eccentricity. Our moment isn't precisely around the major axis. Maybe it's got a little small component around the minor axis as well. In reality, it's probably a combination of the two. But for now, let's just assume that the moment is all about the major axis, but we do have some type of a minor, small type of imperfection in the member. All right, so here we go. So what I wanted to show you, though, is something kind of fun, and it's directly the same thing that occurred in Lecture 1 with column buckling. So here I am. I'm having a look from the top view of our beam. So here's our beam on the right, and I'm having a top view here. I've got the moment applied at one end, the equal and opposite moment applied on the other end, and then I've got an initial imperfection. So I could use anything, maybe a sine curve or something like that. So let's say this is the top flange, and it's got a small initial imperfection. It's going to be small, maybe even just the length, the unbraced length divided by 1,000, some small amount. But then as I start applying these moments, what's going to happen is that small imperfection is starting to grow. So here's the initial imperfection. Here's the deflection caused by the bending moments, and we'll get a total deflection. So if we actually plot this over on the right, and we actually run the numbers or the analysis or whatever and include the initial imperfection and gradually apply, all right, so here we are. We're going to actually monitor the out-of-plane deflection. So on the horizontal axis is the out-of-plane deflection. and on the vertical axis is the moment. So we started with some type of initial imperfection, and then we gradually started applying those end moments, and at first not much is happening. But eventually what's going to happen is those out-of-plane moments are going to grow, and they're going to be amplified by, of course, these second-order effects, the moment on top of the moment. And eventually what's going to happen is we will actually asymptotically approach the elastic critical buckling moment. All right. So this is sort of interesting. This is exactly what happened with columns. But in the column, what AIC decided to do is say, look, we don't want all that deflection, and they limited you to something like 0.877 or whatever's in the column equation, and not letting you get all the way to the Euler buckling load or the elastic buckling load. All right. So I'm getting a request to talk a little bit louder. I apologize. Let me raise my voice here, take a sip of water, and have a go at it. So the bottom line here is that for beams, at least AISC does not really get too excited about this initial imperfection, but it is there. And if you were to do an elastic analysis and gradually apply these moments, the buckling load would approach the elastic bifurcation load, bifurcation moment that we just computed. All right, so that's what it's saying here. So this is the difference between instability and bifurcation. The instability is some type of an imperfection grows until it becomes unbounded, versus bifurcation is you either have no deflection or you've got an unlimited amount of deflection. All right, so that's the sort of the impact that an initial imperfection, what does it do? It causes minor axis bending and some twist. All right, the next assumption I want to undo is linear elastic behavior. So now we're going to say, oh, wait a minute, what about some yielding? All right, so we know that as we, yep.
We have a couple questions back on the torsion stuff. I didn't want to get too far. If we could just cover a couple of them. First of all, the AISC Design Guide 9 on torsional analysis, do they define these warping coefficients, and do they give more values on these?
Yeah, in fact, even in the manual, you know, in the front of the AISC manual, you've got the cross-sectional area, the moment of inertia about each axis. Sitting all the way to the right is the St. Venant J constant and also the C sub W warping coefficient.
Okay.
The only other thing I'd say about that warping term that's in there is you've got to watch, I believe sometimes up at the top of the table it says multiplied by 10 to the 6th or something like that. The warping coefficient does get very large, but those numbers are provided for you for all of our standard shapes.
Okay, and we have a couple more that I want to.
Sure.
So when we're talking about the torsion here, doesn't the torsional moment appear to the supports as well? And how is that taken into account in the derivation of the equations?
Okay. Well, interestingly enough, as we move across the member, so if you go to the next slide, I think we'll be able to see from the top view, you'll be able to see the torque. Okay. So what's happening here is as we get closer and closer to the beginning here, I see what you're saying. The torque is pretty much absorbed right into the support. So what we're saying is that's why it's so important that we have these supports that I'm showing here, is because there is, once this section buckles, there is a twist at the supports, and if those two posts on each end aren't there, the whole section is going to tip over and fall. And sometimes you see this happen when it's horrible, they're placing a big, deep bridge girder, and they don't torsionally secure it at its ends before they release the hoisting cable, and just as a result of its own self-weight, the whole section just literally, it starts to flex, starts to pick up a torque, and the whole system just literally tips over. So yes, there is a resisting torque at the ends, but it's not impacting our solution.
Okay, and then since we're in this area, let me see what slide it was, 34 here. Let me pull that up. And that is on this, why is this a negative sign here before the warping term?
Okay. Let me see if I can go back. Yeah, I'm having good luck here. So right here, let's see, I clicked on it. Can you see this picture here? This was sort of a summary of our torsion work. We had the St. Venant torsion and the warping torsion, and I believe your question is why the negative here?
Yes.
Because all right. So, well, one, the negative is this whole expression is what I substituted in out there. The negative is kind of interesting because if you take a look at it, you think, well, wait a minute. I thought the two of them were going to be helping each other. It seems like this negative is sort of detracting from the conversation or the contribution. Well, as it turns out, if you take a look at theta x, here you're taking one derivative, and here you're taking two more. So we know that these things are always ending up as sines and cosines. So if I have cosine here, if I take two derivatives of cosine, I'm going to end up with a negative sign. And that negative sign is going to offset this one, so they actually become positive.
Okay, thank you. So we will get back into the presentation, and let me bring you to where we were. And I think we're right here.
All right, I'm just trying to catch up in my notes as well here. So, good. Okay, so our next stop then was trying to undo this assumption of linear elastic behavior. Much earlier in the presentation, I showed that before we can even form a plastic hinge, we're going to get some partial yielding. So what could possibly happen is we could get some partial yielding due to the bending moment, and that partial yielding then kills our elastic modulus E. It sets it to 0, so we've actually lost some of the minor axis bending and torsional resistance, and we can really get ourselves a much lower buckling load than elastic LTB. So here we go. So partial yielding of the cross-section. As we apply the moment, the cross-section may begin to yield. This could be due to, one, the major axis bending moment, most likely the case. If there's a small amount of imperfection or a small amount of minor axis bending coming along with it, that is also going to contribute to the possibility of some partial yielding. And then finally, we talked about this torsion. St. Venant torsion does not produce any along the length stresses, but if you think about the warping, it's doing that cross-flange bending, and as a result of the cross-flange bending, those bending stresses are in direct alignment with the major and minor axis bending stresses, so they also contribute to the possibility of some yielding. In the first lecture, and Perry talked about it briefly as well, this yielding is also accentuated by the presence of residual stresses. And any time you've got yielding, you've got a loss in material stiffness, and a loss in material stiffness means that you may have buckling well below elastic buckling and into what we might call inelastic lateral torsional buckling. I tried to do a pretty solid review of residual stresses in the first lecture. Again, just showing you once that wide flange has been rolled and set off to cool, you get some differential cooling. And the flange tips, which have plenty of surface area around them, want to cool first, and they do, and they set. The areas like where the flange and web intersect, they're going to cool at a later time. When they cool, they want to contract, but the flange tips have already set, and you end up with kind of a push-me-pull-me. And so the interior section is trying to contract, and it ends up in tension. And the exterior, the flange tips, are preventing the interior from contracting, so they end up in compression. All right, so that's what those residual stresses were. And even though it's in my cartoon I'm showing you over here, more realistically they are sort of nice and happily distributed throughout the cross-section. But they're real, and they're there, and they're on the order, they could be on the order of 30% of the yield strength of the material. So they're a fairly significant number. All right, so here again I'm showing now this slide which I showed very early in the presentation where we applied the major axis bending moment just to a short beam, and I said that you get some yielding started here. In reality, and especially for minor axis bending, the yielding is going to start down here. And the reason for that, I'm trying to show over on the right here, is before you even put any moment at all into the section, you've got residual stress, a significant amount of stress in compression, say, out at those flange tips. So then you add your M over S, additional stress due to bending, and it's not too long before you get to the yield. And you certainly get to the yield at a value lower than the M sub Y value. All right, so here is the moment it takes with residual stresses to yield this section. All right. Well, I showed this plot earlier. This is when we applied the moments to the beam, and we watched what happened with the initial imperfection, and we watched it amplify. So a few slides ago, we saw the elastic moment approach the elastic critical buckling load. Well, if you were to get some yielding as you're coming along, so you're putting the moment on there and suddenly you've got some yield, well then once there's yielding, the section's going to lose stiffness, and once it starts losing stiffness, you're going to get more deflection, out of plane deflection, so you'll get what we're calling here an inelastic response, and this will asymptotically approach what we might call the inelastic lateral torsional buckling. Now, the inelastic lateral torsional buckling isn't something real easy to calculate and give you a nice, happy, closed form expression for. So we'll play with this a little bit more in a moment. So we've got the elastic lateral torsional buckling occurring, say, here, the inelastic lateral torsional buckling occurring at a moment here. And you might be wondering, well, where could M sub P be? Well, for a real long beam, you'd never be able to get to M sub P before you'd elastically buckle it. If you had a short or intermediate length beam, again, you wouldn't be able to get to M sub P before you'd have inelastic LTB. So there's a couple of different possibilities where M sub P could be located. And I'm going to try to show that to you in the next slide here when we sort of plot up a moment curve. So here we go, our third take at a beam curve. Things have really come together now. We've got full plastic moment capacity. We have the elastic critical moment. Now, we didn't reduce it to account for any initial imperfections, so we're going to stick with that. But somewhere in between here, we're going to go with a transition from the full plastic moment to the elastic buckling moment, and we're going to call that the inelastic lateral torsional buckling moment. Now, the transition really starts pretty much from the beginning, but there is a kind of a long plateau here in which the inelastic LTB is very slight, and you could actually, for some unbraced lengths, up to what we call L sub P, you could sustain the full plastic moment capacity. But once you get beyond the L sub P value, then you're going to get into inelastic lateral torsional buckling. But eventually the unbraced length, again the length between the brace points shown over on the figure on the right here, the unbraced length will get long enough that no matter how much moment you put in there, you won't yield it before it buckles. And that was what we had defined as M sub R in our previous slide, the amount of moment it takes to just cause initial yielding and including residual stresses. All right. So a couple questions might come to mind then is where did LP and LR come from, and what about those assumptions? Well, LR is an easy one to tell you where it came from. It's basically the transition point from inelastic to elastic LTB. And what we basically do then is we know the moment required to produce initial yielding. That's the section modulus times the yield minus the residual, so out at the flange tip. So that's the moment to cause initial yield. And over on the right is the moment required for elastic LTB. And we break out the chainsaw, and eventually we can cut free L sub B. And L sub B solve for L sub B, and L sub B would be what LR is. And unfortunately, it's one heck of an ugly equation. It's really ugly in today's specification, but even a few years back, I stole this one from a previous edition of the LRFD manual. And you can see you've got your work cut out for you, but it's there. And you can see the term here, right here in the specification, the yield strength minus the residual stress times the SX. So it's exactly coming from where we are. So LR and MR is that transition from inelastic LTB to elastic LTB. Where did LP come from? That one's a little bit more difficult. This transition from full yielding into inelastic LTB, well, it didn't come from an AISC cigar room, with people, cigar-filled room with people playing darts. It really varies from code to code. and is completely based on analytical and experimental studies. AISCs, the equation we've been using is this one here, 1.76 times the minor axis radius of gyration times the square root of E over Fy. So I thought you might find it interesting. Well, what happens now if we fire up the finite element program and have a look here? And you can see that these are the finite element results. I've got a wide flange shape modeled by finite element. I've got an initial out-of-plane imperfection, an initial twist, and some residual stresses. I apply the uniform bending moment over a whole range of different L sub B's, and sure enough, I'm getting different curves for depending on this section size. All right. So interesting there. We've sort of finished everything here, except for we've got one more assumption to undo. Well, actually two more. One has to do with the moment distribution. So we have been assuming then that on both ends we have equal and opposite moments. What if we don't have that uniform moment? All right. Now, why did we consider the uniform moment case? Well, as it turns out, the uniform moment case is actually the simplest differential equation to develop and solve. So if you try to do the other ones, they really get ugly fast. It's also the most conservative one, because with that uniform bending moment, the maximum compressive stress occurs in the top flange, and it's the same value along the whole length of the beam. All right? Any other type of a moment distribution that's non-uniform, you're going to have that maximum compressive stress just over a local area, and it will be less in other places. So in place of formulating and solving for all the other possible moment distributions, folks have sort of adequately approximated by scaling the solution to the inelastic or elastic LTB. So taking and scaling that solution that we derived earlier seems to be a favorite way to go about here. So here I am showing you the uniform bending moment case. Like I said, the moment diagram is constant along the length. It's maximum everywhere. And the compression flange is at its maximum stress everywhere. And we solved for this early in the presentation and got the elastic bending moment. Over on the right here, I've changed it up. I don't have end moments. I now have a concentrated load in the middle. I get a moment diagram that looks like this. And it's only in this area right here that the flanges are at that maximum stress. Towards the ends, the flanges on the compression side are not in a large amount. So you see I've tried to vary my C's to show you that the compression is getting smaller in the flanges as we move towards the end. So we'd only expect it to have a larger lateral torsional buckling capacity. And the rule of thumb then is that what we'll do is we'll just scale the elastic solution by some C sub B coefficient. The next slide is just looking at a different case, and this is a case where we've got moment gradient, and in this case, the compression side on this first half of the beam is on the top flange, and on the second half it's on the bottom flange. All right, so we would expect once again to have more capacity in this beam than before, and like I said, the codes seem to go with using a scale factor, a C sub B factor. So a little bit about that C sub B factor. What we're basically going to do is take the nominal capacity for uniform moment, and we're going to scale it by C sub B. And the important thing to note that is under no conditions should we be able to exceed MP. So we can't get right, no matter what, we can never get higher than the plastic moment capacity. There's lots of different equations out there. This is the one that AISC uses, where they more or less sample the moments as you move along the span of the member. And based on the moment distribution from sampling, you can sort of back calculate or estimate a C sub B factor. Wong and Driver provided an excellent summary of all the C sub B factors in the world, really. And this is in a 2010 AISA EJ paper, Engineering Journal paper. And this is a key photo figure out of their paper. And what this shows is for all the different specifications, they were from Canada, so they went first. Here's AISC 2005, which is the same as 2010, the British, the Australian, the Eurocode proposed. And you can see that for uniform bending, everyone's sort of agreeing. But when we get to a significant amount of non-uniform bending over on the right here, so there's this K factor here, or a kappa, which is sort of indicating how much. So when kappa, say, is +1, the moments are in the same direction, and you've got this sort of bending. But kappa could be 0.5 or whatever. And you can see that the AISC are really underestimating compared to the rest of the free world and finite element what the C sub B factor could be. So AISC is very conservative here, where something like the Eurocode is quite liberal in the C sub B factor that you could use. Let's see. So final take, we've now got our beam curve. We're basically developed the strength curve, and M sub n, it includes full yield, inelastic LTB, and elastic LTB. The elastic LTB is based on that bifurcation solution we developed. And if you've got anything but uniform moment, you can scale it by a C sub B factor. So a lot of times I have people ask me, is it conservative to use C sub B equals 1 in all cases? Absolutely, because you're simply not taking advantage of the fact that you do have moment gradient in the beam. A little bit about the brace conditions at the ends. Let's start changing that up. So I want to just show you a couple examples here. First of all, braces are not vertical supports, and they don't have to be vertical supports. All right. Braces are simply here to restrain twist and, if possible, provide some resistance to lateral movement. But the big ticket is restraining the twist. Okay. Now what you've got to do is once you include a brace, well, now you've got two unbraced portions. In this case, portion A, the left side, or span A and span B. And you need to confirm that the math on both spans, because in this case here, the unbraced length in span A is longer than the unbraced length in span B, but the C sub B factor is different between the two. And so you can't just look at it and say, man, I've got this. It's always span A or span B. You really need to be checking both against the capacity. And there'll be more about bracing in lectures 7 and 8. So here I thought you might find an example that we come across quite often, and that is folks want to say an inflection point can just be simply treated as a brace point. Right? And I want to show you that that's a pretty scary scenario to play out. So here we have a beam subject to equal moments, and so this beam is in reverse curvature, and at the center of the beam is an inflection point. So the unbraced length is still L. It's the difference between the brace points. It's not out to the inflection point. If we calculate the C sub B factor there, we would get 2.27 using the AISC equation. So I've got this 40-foot long W24 by 68. And I calculate it's 40 feet makes it elastic. And I calculate my C sub B factor on the left here, 2.7, and I get a critical moment of 319. Now if I go back and I actually apply braces here, torsional braces in the center, all right, one, my C sub B factor did take a hit. It went from 2.27 down to 1.67, but my unbraced length got a lot shorter. Okay. So here's C sub B smaller, but the unbraced length went from 40 to 20 feet. And if you actually do the mathematics here, you would find that the critical moment is substantially larger by providing the brace at the inflection point than not having the brace at the inflection point. I figured you might have some fun, and I did the same thing in the finite element world and showed you basically what the finite element program would calculate. So here we are applying the moments and getting the buckling load according to finite element, and it's coming in at 382 kip feet. And if you take a look here, the red is the top flange, and the blue is the bottom flange in the top view. All right, so it's kind of interesting to try to, in your brain, visualize the deformed shape. But again, we have an inflection point at midpoint. If we apply a brace at that midpoint and then do our buckling analysis, then things get very interesting. You can see that sort of the length on the compression flange was this long, lots of length in the buckled mode. Because that brace, the buckling has to go through the brace point, and we've significantly reduced sort of the buckling length. And with this significant reduction in the buckling length, we get a real bang for our buck and a significantly increased moment capacity. So what's the takeaway here is that an inflection point is not a brace point. All right? And so I'll let you wrestle in your mind with why does the AISC only give you 677 in that example, but the finite element gives you so much more. And I'll give you one little hint. Think about continuity. All right, so we've gone through our lateral torsional buckling, and we've undone all the important assumptions. And I want to then finish up by just taking a look at some of the beam curves. All right, so the landing gear is down. We're coming in for the finish. Let's have a look first at the AISC flexural strength. Again, AISC defines the moment at first yield, and they're assuming here from this equation that it's about 70% of the yield moment, which means 30% of that is absorbed due to residual stresses. From that, they back calculate an L sub R, like I was saying earlier. We also have an equation for L sub P. So for short unbraced lengths, AISC says for those you can get to the full plastic moment capacity, which is Z times sigma Y. For really long unbraced lengths, larger than the amount it would take to yield the section, you can get to the elastic. So this kind of crazy looking equation is the one we derived earlier. It scales by C sub B to account for moment gradient, and that's your capacity. Unless it exceeds MP, then your capacity is limited to MP. And then on the in-between, it's sort of interesting. Instead of even trying to find out what's going on there, AISC punted and said, oh, let's just keep this easy and just do a linear interpolation. So this is just an equation interpolating between LP and LR to determine what the capacity is. So here's sort of a picture of that from the AISC commentary. For short unbraced lengths, you can get to MP. For longer unbraced lengths, you can get to the elastic critical buckling moment we derived. And in between, we just take the points LP and MP and LR and MR, both of which we can compute, and we interpolate. Now LR and LP, especially LR, is a real drag to calculate. So in the manual, the AISC has provided you all the charts for the beam diagrams for all the different shapes. And my students get so excited when they see that after having one homework where they actually have to compute LR and everything, that they usually Xerox it and make it a poster in their dorm room. We used to hang up posters of different things, but now it's the AISC beam charts. Very exciting. Well, anyway, how does the AISC curve compare with finite element? And you can see that the finite element shows smaller strengths than AISC. Now we don't have any phi factors here, so no reason to panic. And I'm also only showing the case for uniform moment. Now these are the analytical curves. The experimental curves are always above, they seem to always be above the analytical curves, and certainly then would be closer to AISC. Now this is one of my favorite slides in the presentation, because what it shows is the strength curves, the beam flexural strength curves for really all the different specifications in the world. So the one we were looking at was for a doubly symmetric section, the AISC one. That's the solid red one. We've got the Canadian curve. Now the Canadians are even more liberal than we are. So they're providing more strength in that inelastic LTB area. The Australians sort of match us fairly well, but they actually include, as do the Europeans, who are the curves that are well below the American codes, they actually include the initial imperfection in account for it. So they have a reduced strength. So when you look at this picture, you might say, wow, the AISC is so liberal and the Eurocode is so conservative. But actually keep in mind that the AISC was very conservative with their C sub B factor, where the Eurocode was very liberal with it. So I think in the wash, as long as you've got some moment gradient, which is almost always the case, the specifications are really giving essentially the same amount of capacity. So a bit of a summary. Tonight we looked at the limit states of flexural members. We focused on full yielding and lateral torsional buckling. We did not have an opportunity to see what happens if there's a possibility of local buckling, but it's not usually the case. We went from lateral torsional buckling theory to flexural beam strength curves, either by AISC or others. Our beam curve, whether it's in our own specification or others in the world, does account for full yielding. It does account for some loss in stiffness due to initial imperfections or out of straightness. It does account for partial yielding accentuated by residual stresses. And with that C sub B factor and the L sub B, it does account for moment gradient and the location of braces. And of course, we also had the opportunity to take a look at the AIC and other standards. That's pretty much my lecture tonight. It's been a pleasure speaking with you. Next week, Todd's going to give us some information on designing flexural members. So he'll take what I did and provide you lots of neat design examples.
Okay, thank you, Ron. We do have some questions, and we do have time for a couple of questions. So why don't we do that right now? The first one's going to be, how does the location of the load influence the capacity? For example, if you had a load at the bottom flange versus the top flange.
Right. I'm going to give you the quick answer to that, and I believe I've seen Todd's presentation for next week where he's going to talk about it a little bit more, because it does, indirectly, you can sort of trigger a different C sub B factor with it. But certainly, if you, for the examples I was showing, if you put, say, the concentrated load at midspan instead of on the top flange, on the compression flange, you hang it from the tension flange, you do increase the capacity of the member. And Todd's going to talk a little bit about showing how that is. But it would only make sense when you're hanging the load from the bottom, you're sort of pulling the member down and straightening it and trying to resist the LTB, where when the load's on the top, and you start to get any type of out-of-plane movement, that load is even going to, almost through a second-order effect, is even going to accentuate that. So load placement is definitely important. In general, AISC doesn't account for it with its C sub B factor, but I suppose, that's where they say, or by rational analysis. So you could account for the load placement through a rational analysis and use a different C sub B factor. But Todd's going to speak about that, I'm pretty sure, next week.
Okay, great. Now, speaking of C sub B, can C sub B be less than 1? Someone's mentioning here that they had heard that if the applied load is higher than the shear center, that C sub B could be less than 1.
That's a good one. I might punt to Todd next week on that to talk more about it. Certainly, if you had the load, all of the work we did was assuming that the load was very close to the centroid. But certainly, if the load was like on a post that was well above the centroid or in a section in which you weren't getting there, there could be an overturning effect produced by that load being so far away from the neutral axis. We tend to call it a C sub B factor. Technically, the C sub B factor is for moment gradient, but purely speaking, if the C sub B factor is for moment gradient only, it can't be less than 1. But if you're going to let it go and account for other things like load placement along the height, then I suppose it could be.
Okay, thank you. And then do we need to brace the top and the bottom flange in order to reduce the unbraced length?
Okay. Again, Todd Helwig and Joe Ure are going to speak about bracing in lectures 7 and 8. The key, the response I want to give, and I almost feel like a bit of a politician here, is I just want to indicate what you're trying to do is resist twist. All right. So if you can develop some type of a mechanism between the tension flange and some type of a brace point, maybe it's even coming into the neutral axis, out of plane brace point, but as long as you can sort of try to develop some type of resistance to twist, you're going to get a nice bracing solution. But the details on how to do that, man, they're coming for you in lectures 7 and 8. Be patient. You're going to get some good stuff.
Okay, good. We do have a question on one of the earlier slides, so I want to go back to slide 37.
These are great questions. Great questions.
Okay. So this, on slide 37 here, where we're talking about M sub E,
Yeah, the elastic moment. Yep.
Yeah. Is this M sub E the M critical that's in the AISC specification?
Aha. Yes, it is. If the person there has the 2010 specification, I believe if they look on the next page, they'll see a user note that provides this equation, and the user note effectively says that big ugly equation on the previous page, which is trying to also give you elastic LTB moment for channels as well, reduces to the equation I'm showing for wide flange sections. So yeah, they're the same thing. And again, that's even one of my assignments for the students is to give them the really ugly one, and then tell them, now, wasn't it worth just turning the page over and seeing that user note that tells you for wide flange shapes, you can just use this more simple equation. But they'll give the same results.
Okay, well, good. Well, thank you, Ron. We have run a couple minutes over, so I want to just go through quickly, but I want to thank you first of all.
Oh, you're welcome.
I want to go through quickly our CEUs and the other material for you. Remember, if you signed up for the individual registration, that was the $185, where everyone is getting a CEU. You will be receiving an email from ceu@aisc.org within 2 business days, and please follow the directions on that email. The 8th session registrants, you will get your CEU certificate at the conclusion of all of the 8 sessions. Also, for the 8th session registrants, you will be getting an email by Wednesday, June 19th, this Wednesday, and it's going to contain a link to the quiz as well as the recording. The email is going to come from nightschool@aisc.org. The reasons you would want to take the quiz is if you want EEU credit, you must take all quizzes and the final to receive the EEU, the equivalent educational unit. If you cannot watch one of the live sessions and you watch the session recorded, you must take the quiz and pass the quiz in order to obtain CEU credits. If you watch the live session, you do not need to take the quiz to obtain CEU credits, but we do recommend taking the quiz because it does reinforce what you learned tonight. Also in that email, you will have access to the recording, and again, that's coming by Wednesday, this Wednesday, and it's coming from nightschool@aisc.org. The recording will be available until July 1st for this session. Here we have a typical quiz and recording schedule. The quiz and recording access, as I said, it will be 2 days after the live session. It will be this Wednesday you will get access, an email. The quiz due date is the 2nd Friday after the live session. Quiz scores are posted every Monday, and I will get into how you can see where they are posted, but they are updated every Monday. You can retake the quiz, and that due date is the 3rd Friday after the live session. And the final quiz scores and answers posted 3 weeks after the live session. So to want to see your attendance and quiz scores, you go to aisc.org/nightschool, and on the left-hand side of the page, you click on Current Course Details. And when you click on Current Course Details, you roll down to the bottom of that page, and you'll see a table like this that is getting filled out, and you'll see links to the quiz and attendance. You click on those links, and you can find your quiz and attendance scores, your quiz scores and your attendance record. So with that, I would like to thank everyone for attending, and I'd like to again give special thanks to Ron for providing today's presentation.